Alright, I want to solve graphically this linear programming problem. I want to minimize c is equal to 12x plus 4y, subject to the constraints x plus 3y is greater than or equal to 9, x plus y is greater than or equal to 6, and x is greater than 0 and y is greater than 0. So to solve this, I start by graphing the feasible region, the solution to these inequalities. The first equation, I'm going to treat that as an equation and look for the intercepts. If x is 0, y is going to be 3. And if y is 0, x would equal 9. So that first equation is going to connect those 2 points, 3 and 9. And if you try 0, 0 in there, you'll see that 0, 0 is not an equation. If you plug in 0 for x and 0 for y, you'll get 0 is greater than or equal to 9, which is a false statement. So I know that my solution region is outside of that area. All right, the next inequality says that x plus y is greater than or equal to 6. So if x is equal to 0, y would equal 6. We're going to cross the y-axis at 6. And we're going to cross the x-axis at 6, 0, 0, 6. So 0, 6, and 6, 0 is that equation as well. And the 2 points, it looks like they're intersecting here at 5, 1 is my general guess for that. I know that 5 plus 1 is equal to 6, and 5 plus 3 times 1 is not 6. So they're not intersecting at 5, 1. Let me actually solve it. Let's take this as an x plus 3y equals 9 and an x plus y equals 6. I want to solve that. I'm going to solve by elimination. I'm going to subtract. I'm going to subtract the second equation from the first equation, and that'll give me 2y is equal to 3. So y is actually 3 halves. All right, and if y is equal to 3 halves, then x would equal, well, I know that x plus 3 halves is equal to 6. So x is equal to 6, take away 3 halves. So that's 12 halves minus 3 halves, it's 9 halves. So it looks like I'm at the intersection point here is 9 halves, 3 halves. So 4 1/2, 1 1/2 would be that intersection point there. And the feasible region, again with that x plus y is greater than or equal to 6, 0, 0 is not going to be a solution. If you sub in 0 for x and 0 for y, you'll get 0, and 0 is not greater than 6. So I don't want the 0, 0 side. I want the opposite side. So it looks like my feasible region is this unbounded region out here. All right. The corner points that I'm looking at are this one over here, 0, 6. I've got the point 9 halves, 3 halves, and 9, 0 are the corner points. And our fundamental theorem of linear programming says that those extreme values occur at the corner points. And so I have 0, 6, 9 halves, 3 halves, and 9, 0. I want to try each of those into my C formula, the objective formula, which is 12x plus 4y. If I plug in 0 for x and 6 for y, I should just get 24 there. If I plug in 9 halves and 3 halves, 9 halves times 12, let me reverse that order in there. I want to do 12 times 9 halves plus 4 times 3 halves, and that will give me, what will that give me? 6 times 9, 54 plus 6. 54 plus 6 gives us 60. Total of 60 there. And if I try 9, 0, 12 times 9 plus 4 times 0. 12 times 9 is 84. No. 108. 12 times 9 is 108. And so what I'm trying to do is find the minimum. Again, we're trying to minimize C, and so the smallest value I have is 24, and it's occurring at the 0, 6 point. So we have a minimum of C equals 24 at the point 0, 6.